Good afternoon, everyone, and welcome to the EOL seminar series. I am pleased to welcome back Dr. Joshua Gebauer, who recently completed an NCAR postdoc at EOL, working with Steve Onkley at the In Situ Sensing Facility. Currently, Dr. Gebauer is with the Cooperative Institute for Severe and High Impact Weather Research and Operations based out of the University of Oklahoma. Oklahoma plays a significant role in Josh's academic career. He is a graduate from the University of Oklahoma with both a master's and doctorate degree in meteorology in Alan Shapiro's group. While at OU, Josh honed his knowledge in boundary layer meteorology using observations from scanning radars. In particular, Josh has developed expertise in working with the CLAMPS system. CLAMPS stands for Collaborative Lower Atmospheric Mobile Profiling System that houses several remote sensors that include the Doppler Lidar, the atmospheric emitted radiance interferometer, also known as AERIs, and a microwave radiometer. Prior to his postdoc, Josh has worked with EOL operating clamps in the field during Pecan and Perdigao. During his postdoc at EOL, Dr. Gebauer participated in the Lotus 2021 field campaign out at NCAR's Marshall site that tested a prototype of a single intensive sensor network that included the clamp system and EOL platforms from ISFS, ISS, and MPD. Using such a suite of high temporal resolution observations of water vapor, temperature, and wind profiles within the boundary layer is critical to understand how weather in the lower troposphere evolves. It is results and ideas from this field campaign that Josh will be talking about in his seminar. His talk is titled Methods and Strategies for Multi-Instrument Data Products in Next Generation Boundary Layer Observation Networks. We are using Slido to post questions, which you can type in at any time during the seminar. The Slido window is located below this presentation screen. We archive all questions until the end of the speaker's presentation, where they will be revealed during the Q&A portion of the talk. Dr. Josh Gebauer, we welcome you back to EOL, and the virtual stage is now yours.
Thank you. Thanks everybody for logging in today to listen to my talk. Just a fair warning, I'm currently on the recovery side of COVID right now, so there might be times during this presentation where I have to stop and cough for a bit, but I'll get through it, and hopefully they're few and far between. Most of this work that I'm going to be talking about today was done while I was a postdoc at NCAR, but there's a little bit that I've been doing while since transitioning to my job at CIRO. I also want to point out that while at CIRO, that I am also a member of the BLISS group at the National Weather Center, which is just a boundary layer. It stands for Boundary Layer Integrated Sensing and Simulation. And it's a boundary layer group that is kind of trying to bring together boundary layer scientists from the different organizations in the NWC to kind of foster a good boundary layer development at the University of Oklahoma. Before I get started with the talk, I wanted to point out that there are a lot of contributors to what I'm going to be talking about today. Lots of people at EOL, people at different NOAA labs, people at the University of Oklahoma, and also at other labs in NCAR. So I have had a ton of help working on all of these ideas that I'm going to be talking about today. I just wanted to show all of the people that have helped out with this work. So when we think about boundary layer observations, the boundary layer is a quite difficult thing to observe, mainly because there's not a single instrument that can provide thermodynamic and kinematic profiles for the entire depth of the boundary layer at the spatial and temporal resolution that is really needed. And the first thing everyone thinks about when they think about profiling in general is radiosondes. And radiosondes provide horizontal wind, temperature, and humidity, and they definitely travel throughout the depth of the boundary layer. But really, they're not the best thing for profiling the boundary layer that we have. it is considered the gold standard for profiling, and there is a reason why I'm comparing the profiles I'll be showing today to radiosonde observations. But radiosondes really are not a true vertical profile. Uh, they don't really get you vertical velocity that you at the temporal resolution that you would need to measure things that you care about in the boundary layer. You need constant staffing to launch radiosondes, unless you develop an automated launch system. But that, to me, sounds like a lot of moving parts that might need constant staffing to fix anyway. And it's not really feasible to launch radiosondes frequently enough to capture all the boundary layer phenomenon that you might be looking at. Say you're in a stable boundary layer and you want to observe gravity waves, it's going to be pretty difficult to launch radiosondes frequently enough through the gravity wave to understand it. Beyond radiosondes, we have things like instrumented towers, where these provide very high temporal resolution observations of temperature, humidity, wind, and any other instruments that you can put on the tower to measure things like trace gases too. And we're able to obtain these observations very close to the surface, which not many instruments can do. But an instrumented tower can only measure up to the height of the top of the tower. And the difficulty to set up a tower is going to be proportional to the height of the tower. And there's also things like sighting that is difficult with these. So instrumented towers, while they have the temporal resolution that they need, they really can't get you to the top of the boundary layer that you might want. But we also have remote observations remote profiling observations from things like Lidars, where advanced scanning Lidars can retrieve winds up to 1 to 2 kilometers pretty easily. And it feels like Lidar technology these days is advancing very rapidly. And that the height that you can get scanning with them seems to grow by the year. They're very useful for measuring things like vertical velocities throughout the boundary layer. And you can scan pretty rapidly with them. But any winds that you obtain with the LiDAR are actually from a wind retrieval, usually from a VAD or DBS. So your retrievals are going to degrade with height. You also have blind ranges associated with LiDARs, and LiDAR returns depend on aerosols. So if you take a LiDAR up into high altitudes in the middle of winter, you're going to have a hard time getting any returns to measure your winds. So they aren't always going to be the most useful instrument for measuring winds. And then there's things like radar wind profiles, which you can provide wind profiles all the way up to the mid levels of the atmosphere. But your first data level is hundreds of meters above the ground. Your vertical resolution is getting to the edge of where you actually probably want it in the boundary layer profiling. And you can only obtain profiles, depending on the type of radar wind profile you're using, about every 5 to 30 minutes, which is probably a little bit slower than you would want. Now, getting into the temperature side of things, we have things like infrared spectrometers. This is your AERIs and your assists. These can provide high temporal resolution profiles of temperature and water vapor, but these temperature and water vapor profiles are coming from atmospheric radiances, which those retrievals are an ill-posed problem. Most of your information content from in those retrievals is at your lowest levels, and your effective resolution of these profiles is increasing with height. So those themselves are also not the answer. You have microwave radiometers, which are similar to the infrared spectrometers, but operating in the microwave. They can provide maybe a little bit more information through clouds than infrared spectrometers, because the microwave travels through clouds better than the infrared. But the retrievals have similar cons as the infrared spectrometers. It's an ill-posed problem. There's fewer channels that you're retrieving the profiles with. And microwave radiometers require frequent calibration, which can be hard to keep up with. And then we have what at EOL is known quite well, things like Micropulse Dial, which you can get high temporal resolution profiles of water vapor, but there's low-level data gaps. And for now, I know from my time at EOL that there is an effort to add temperature profiling to Micropulse Dial. There is no temperature data that you get from it. So there's a whole bunch of instruments that we have that all have their kind of niche in measuring the boundary layer. And I haven't even listed all of them. For example, I should have probably created a slide for UAS, since that is definitely an emerging technology used for sensing the boundary layer. But all of these instruments have their own kind of sweet spot for observing something in the boundary layer. So this plot here is just something I took from my time at EOL. It's been associated with the Lotus idea for quite a while, and it just shows the different instruments that would be at a Lotus profiling node, and shows how when we combine all of those instruments together at a single site, we're able to obtain boundary layer profiles from the surface all the way up to the top of the boundary layer, and even beyond that, about to the mid levels. But so when you have this type of profile at a single spot, that's really good. But why would you stop at just one of these, stop at just one profiling site like this? So that's kind of the idea behind the next generation boundary layer observation network. We want the ability to sense the full profile of the boundary layer, but we also want to be able to do quasi 3D sensing of the lower atmosphere. And why would we need such a network? Well, first of all, the most important and interesting meteorological phenomenon that exist are associated with gradients. So if we don't have multiple sites, it can be very difficult to observe those gradients that are important for the phenomenon that we might be looking at. Having a network like this can improve boundary layer parameterizations in NWP because we have multiple observations at different locations. So we're not relying on creating parameterizations just based off of one site in a certain region. We also will be able to provide observation for data assimilation studies. These networks have already started to show that they provide quite a bit of value to potential forecasts that assimilate data from sites that have multiple profiling sites in them. So those are just a couple of reasons why next generation boundary layer observation networks are important. But these boundary layer networks require the development of data products that provide value beyond just the collection of observation from the observations from the individual instruments. So it's great to have all of these observations at a single location, but it's kind of difficult to use all of these observations in their kind of piece by piece state when they're just all thrown together at a site. Most of the value in using these observations is going to come from combining the strengths of the different instruments together to create a product that will be most beneficial to the end user. And this talk today is going to focus mostly on creating these data products at those single individual profiling sites. But I wanted to talk a little bit before that the idea is also that we have multiple of these profiling sites in the future. But I am a firm believer that in order to before we start trying to go in the spatial dimension and creating these data products, we first have to make sure that we can get good data products at the individual profiling sites by themselves. So before I get into what I've been doing, I have to introduce something called TropoE. And TropoE stands for Tropospheric Remotely Observed Profiling via Optimal Estimation. You've probably heard of TropoE in the past, except it wasn't called TropoE then. It was initially published as AERIs by Turner and Leonhardt 2014. It was upgraded to AERIs version 2 by Turner and Bloomberg 2019. And the idea behind AERIs was initially to take airy radiances and to be able to turn them into temperature and water vapor profiles. But in 2019, AERIs was ported from IDL to Python and renamed to TropoE. And the reason for this port to Python was it first allows more people to use the retrieval because we can get away from having to be constrained by the IDL licenses. The meteorology community is moving towards Python. So that also increases potential future contributors to TropoE and also potential people that will use it. If you're more familiar with Python, it might be easier for someone to grab a Python program than one that was originally written in IDL. And also the name was changed really just to highlight that it works with more than just AERI data. And I'll get into that in the future, but TropoE also works with microwave radiometers, and we can put all types of data through this thermodynamic retrieval. So how does TropoE work? Well, it's a physical iterative thermodynamic retrieval that uses optimal estimation. And optimal estimation is an inverse retrieval method that's based off Bayes' theorem. And we have to have three assumptions that all of our errors in our observations and our priors, they're represented by Gaussians. If our errors are unbiased and we have forward operators that are mostly linear, which is not an assumption that really is valid when doing thermodynamic retrievals from radiances. Using those assumptions with Bayes' theorems, you can derive equations to retrieve the state vector and the uncertainties for that updated state vector. So this looks a lot like data assimilation, and that's because it really is basically data assimilation, but without a model. We're using a prior state vector that's coming from climatological radiosonde data, and then we're using observations from, initially it was just infrared spectrometers, but you can almost put anything into that observation matrix. And that's kind of what I'm going to be showing today. But you have a prior state vector, you have then your retrieved state vector, things like your error covariance matrices for your prior, your error covariance matrices for observations. You have a Jacobian matrix, which is just how that forward operator is changing with a change in your state vector, and an observation vector, and your error covariance matrix for a solution. So like I said, it's very similar. It has a lot of the same terms as data assimilation. I also want to point out that the equations that I'm showing here are iterative to account for nonlinearity in the forward model. So that's how we kind of skirt by the problem of that our forward model isn't always linear. So why am I talking so much about TropoE? And I kind of alluded to it a little bit already, but TropoE is an excellent tool for combining observations from multiple platforms. And the best example for this would be to see the Turner and Lonehart paper that came out in 2021 that combines AERI data, microwave radiometer data, and MPD data, and shows that by combining all of those observations together, you can retrieve a better thermodynamic profile than from just the AERI or just the microwave radiometer. And it also seems to improve in the water vapor part as well from just dial observations. So any observation can really be used in the observation vector, as long as you can quantify what the measurement error can possibly be. And as long as that instrument's unbiased and you can make a forward model for the observation, there's no reason why that observation can't be put into the retrieval. These observations are going to be optimally combined to produce the best possible thermodynamic profile. Of course, that's in theory. And the retrieval will provide uncertainty information so the user can know which regions of the profile are well constrained by the observations. And then beyond just uncertainty information, you can get information about, from the degrees of freedom, where you actually have the most information content from the observations in the profiles. So it's actually a very useful data product for the situation for these next generation boundary layer observation networks. So I did a lot of talking about what we could use to do thermodynamic profiling, but what about for wind profiling? You can actually do the same optimal estimation technique for wind profiling. And this would be quite useful for regions where instruments overlap. For example, the region between Doppler lidars and radar wind profilers, where the Doppler lidar may be starting to lose a good signal and your measurements are starting to get noisy, but your radar wind profiler has good measurements there. What is the best way to optimally combine the information from those two sensors? Well, optimal estimation is one way that you can potentially do that. And so I created a program that I call WindowE. I don't know why I called it WindowE. I guess just wins via optimal estimation, but everyone told me not to change the name that I've talked to so far, so we're just sticking with WindowE for now. This, like I said, I recently created this retrieval, and it's still very much in development mode. And the reason it's mostly in development is that most of the work is currently going into figuring out the best way to properly represent the errors of the measurements. So when working with the data, I have to think about, for example, with a LiDAR, how well the LiDAR is sampling not just the radial velocity, but how much that radial velocity is representative of the actual wind in that at that height. So figuring out how to best do that has been a little bit of a challenge so far, but I'm still working on it. But I'll show some results from window E later as well. So this was talked about a little bit before I came on, but the Lotus 2021 field campaign happened last July, and this was July through August, and this was really a field campaign of opportunity, since most of the instruments that were at EOL at the time were not being used because the field projects had been canceled. So we figured, why not put all of these instruments out at the Marshall Field site and try to create a prototype Lotus node to kind of see what we can do with the observations and see if we can kind of get a head start on how we could make data products for Lotus. And we had a bunch of instruments at the Marshall Field site. We had the 449 wind profiler, we had a 915 wind profiler, the MPD, we had a wind cube, Doppler LiDAR, an instrumented tower. I was able to bring OU's clamp system up to the Marshall Field site. And then we also had Radiosondes launched as well. So with this data from Lotus 2021, I did a lot of testing with combining the observations from all of these instruments together. Essentially with TropoE, I did a kind of a verification of the results from that Turner and Lonehart paper, where I'm combining AERI, microwave radiometer, and MPD data, which is a good verification to have. The Turner and Lonehart paper was done in Pertigao and in the Central Great Plains. It's good to see if the results still hold up on the Front Range, for example, since these observation networks are not going to just be at one location. Ideally, we're going to be able to deploy them at locations all over the world. So with these, I also ran a set of retrievals where we had an additional wrap model constraint above 4 kilometers. This is just something that's normally done with TropoE retrievals, since there's so little information content above 4 kilometers from the instruments at these sites. And so that just prevents you from having really bad profiles above that can potentially impact your low-level retrievals. And then the Radiosonde launches from the Marshall sites were used as verification for the TropoE retrievals. For the window E retrievals, we ran the retrievals with 30-meter tower data, with the 449 wind profile, and with Doppler LiDAR VAD data. For this, the Radiosondes were used as a comparison for the retrievals, but I didn't really use them as a verification data set, mainly because I didn't feel comfortable using the winds from the Radiosondes as the truth as much as I did for thermodynamic variables. So it's just kind of a comparison to see, is the wind retrieval, the shape of the profile is similar? Are we kind of in the ballpark for right now? And the results of window E are still very much preliminary. So here are some examples of the TropoE profiles from the Marshall site. And these are with no wrap constraint above 4 kilometers. And this is for 12 August 2021. And so when you're looking at this, you can see that for temperature, we get generally consistent temperature profiles between the different sets of observations. On the left is the full profile, and then I'm just zooming in at the lowest 3 kilometers on the right side. You can see that microwave radiometers do not provide as good as a temperature profile as the AERIs do. An interesting result in the temperature profile that happened pretty consistently, and we're not really sure why, is that we got this large warm bias above about 1.5 kilometers when we had the AERI microwave radiometer and MPD all added into the TropoE retrievals. I think this possibly could be related to the calibration of the AERI. After we took the AERI back to OU, it was discovered that the the scene mirror in the area was quite dirty and needed to be replaced. So this could possibly be because of that, but it's pretty consistent, and it actually really ruins the verification statistics of the AERI, MWR, and MPT retrievals quite a bit in the temperature side. When looking at water vapor, though, you can see that the AERI by itself, this blue line, does not do a great job of observing the water vapor profile. And that's just because there's not much information content from just the infrared radiances for the water vapor profiles. But when we add the MPD data to that observation vector, the water vapor profiles look much more like what's being observed by the Radiosonde. And then going forward, I also wanted to show how the uncertainty profiles change with height, and how the uncertainty profiles change when we add in that MPD data. You can see that the temperature uncertainties just kind of increase with height. Also, the uncertainties here clearly don't match up for the MPD AERI microwave radiometer MPD data, where it says it should be the most certain profile, but it's clearly the worst profile out of all of them. But again, that's something I'm still looking into, what could possibly going on. But at the water vapor side, you can see that adding the MPD data, where the MPD data starts to kick in around 500 meters, we get a big decrease in our uncertainty of the water vapor field when we have MPD data going into those TropoE profiles, which is what we would expect, since the MPD does such a good job of giving information on what the water vapor field actually is. And then when you add a wrap constraint into these profiles, you can see what happens. Above 4 kilometers, the wrap is pretty certain about what the temperature and water vapor field is going to be like. So the retrieval, since there isn't really much information coming from the observations, generally just trends towards what the wrap is once you set it to the heights that the wrap profile is being used. And you can see that in this weird snap to this one profile of 4 kilometers in the water vapor field. You can see it does mitigate a little bit that warm bias in the AERI microwave radiometer and MPD data, but it doesn't eliminate it all the way. But this looks pretty similar to what the profiles do look pretty similar to what was there with no wrap constraint. And then you can see with the uncertainty information is that there's less uncertainty with height once we have the wrap, especially in the water vapor field, which makes sense since above 4 kilometers, you have such low water vapor to begin with. There's not much room for there to be uncertainty in the water vapor when you use the model constraint. So now looking at bias plots from the collection of all the radiosondes during the Lotus 2021 campaign. Those previous plots were actually from just one time and one radiosonde. I didn't want to show you every TropoE profile that I created the entire time I was there, but wanted to give a good idea of what the typical profile might look like. And you can see from these bias plots that the AERI only actually provides pretty decent temperature profiling up to 2 kilometers, a little maybe at most to 3 kilometers. When we combine the instruments, again, we get this weird thing at 2 kilometers where we have this high bias in the AERI microwave radiometer and MPD retrievals. In microwave radiometer, retrievals are biased too high at low levels and then are too cold at upper levels. And AERI and MPD does a pretty decent job of retrieving temperature profiles. When we have add in that wrap constraint, you can see that the AERI and wrap data by themselves do a really decent job of profiling what the temperature actually is throughout the boundary layer. And then because the wrap is constraining it, it looks like it's doing really well from 4 to 10. But again, this is mostly just what the profiles are from the wrap analysis. We still have this weird positive bias at 1.5 to 2 when we have microwave radiometer data included. But when we get rid of that microwave radiometer data and we have AERI, MPD, and wrap data, that still looks pretty good, just like the AERI and wrap data. Again, I'm not really sure why that warm nose bias exists. It wasn't seen in the Turner and Lonehart paper. So again, I think it could be due to calibration issues, but it's something I had to look into a little further. It is an interesting conundrum though, because when you look at the mixing ratio plots, as you might expect, the AERI microwave radiometer and MPD data have the best mixing ratio profiles. So is it worth the trade-off of that warm nose bias to get that really good mixing ratio profile? I don't know. That's a great question, and is why I'm hoping it is a calibration issue with the AERI. But the AERI by itself doesn't do a great job of retrieving mixing ratio. The microwave radiometer has its own biases as well. And when we add in that wrap constraint, things again get a little bit weird in those when we have all the instruments together. But the AERI, MPD, and wrap really has a pretty decent mixing ratio profile. So that's some just preliminary work on kind of combining observations together for thermodynamic profiling from the Lotus 2021 campaign. Now I'm going to talk a little bit about my window E retrievals. And again, this is just very preliminary results where we're combining tower data, Lidar data, and observations from the 449 wind profiler. And I do want to point out that currently my retrieval assumes a fixed error for the wind profile data, which kind of limits the accuracy of the retrieval above 1.5 kilometers. This is because I'm still working out what the proper way of, again, measuring the errors associated with the 449. And because the errors aren't properly represented, some regions of the profile are too certain in areas where the data is a little bad, so you get weird. So the profiles deviate more from the radiosonde in the parts where the profile is just relying on the radar wind profile data. But you can see on this plot with U and V that I have pretty good agreement between my window E retrieval and also what the radiosonde is doing. And then just for another case, again, showing where we have observations up to 4 kilometers from combining the all of the instruments together, that there's pretty good agreement between the profiles. And I also want to point out, these are pretty difficult profiles. They don't not look it, but they're pretty difficult profiles for these instruments to retrieve because the winds during the field project were so weak at the Marshall site. It's just hard sometimes to get enough signal to get a good retrieval in low wind environments at times. So I was pretty happy with how the wind retrievals worked during the Lotus 2021 campaign. This is just an example of what the wind retrieval looks like over a whole day during Lotus 2021. And this is, you can see that we can get good observations up to about 3.5 kilometers pretty consistently. It is a little bit more noisy than you might want, but I believe that once I work out the kinks with properly representing the errors in the observations, that those will work themselves out a little bit. So that's just my initial work with just using observations. But now I'm going to talk about my belief of the role of modeling with these next generation boundary layer observation networks. And this is a pretty strong belief I have, is that these future boundary layer networks need to be closely connected with modeling efforts. And I'm going to show an example of why that is the case coming up here. These observations, the observations from these types of network can be used to not only improve models, but models can also be used to create and improve analysis products. For example, modeling, beyond just using the wrap analysis, which was great and works well for what we were using it for, it can still significantly improve our thermodynamic and kinematic retrievals. And I'm going to show you how that is. So I'm going to introduce into TropoE and also window E an ensemble constraint. So with advancements in modeling capabilities, we often have a good idea of what the atmosphere is going to be like at a specific point at a specific time, especially when we use ensembles. If you pick a point and you say, what's the atmosphere going to be like in 12 hours, we have a pretty good understanding of that. So why would we not want to use that information in a retrieval that is an ill-posed problem. That's good information to have when trying to make this retrieval. So we can take forecasts from NWP Ensemble and use that as a constraint in that retrieval. So we put the ensemble mean of the profiles from the ensemble into the state vector, and then we take the covariance from the ensemble members and put them into the air covariance matrix. And as a proof of concept that this idea might work, and with help from Chris Riedel at postdoc in CISL, I did a quick and dirty 50-member WRF ensemble forecast for 5 August 2021, centered on the Marshall site. The reason I picked 5 August 2021 wasn't because anything interesting was happening on that day. It was just the day that I had the most radiosondes that I could use for verification. So it would provide the most bang for my buck for running this ensemble and testing that this type of constraint might work. And the reason I had to make my own ensemble is because publicly available hourly ensemble forecasts don't really grow on trees. There are some experimental ones out there, but they don't often run all the time. And I just wanted to kind of have something that I could kind of tweak at first to see what was going on. But in the future, I would love if there would be something publicly available that we could use for this type of constraint. The forecasts were initialized using the 0 UTC HER analysis for 5 August 2021. And the reason I call it a quick and dirty WRF ensemble is because the spread in the ensemble was created using stochastic physics. Its grid spacing was 3 kilometers, and I want to really point out that this is not an optimal forecasting ensemble. I just wanted to have a way of having a spread develop in an ensemble in a region where we could have an idea of what the temperature and water vapor profiles might be. The nice thing is that because we use stochastic physics, is that most of the spread is developing in the boundary layer. And with anything, this ensemble constraint is always going to be really useful for this type of profiling. Where are ensembles often the most variable? It's going to be in your parameterized regions where you have lots of things that we're uncertain of. So that means that we're going to build up the most uncertainty in our ensemble constraint in the boundary layer, which means that and most of our information from our instruments is coming for the boundary layer. So it's really like a perfect match that the ensemble is most uncertain in the boundary layer, but we have the most certainty from our observations there. And so then, like I said, those hourly ensemble mean and covariances from those forecasts were used as constraints in the retrievals that we did for this day. And when I got the results from just using the AERI data and the model constraint, I was really shocked at how well the profiles looked. And so on the left is just the full profile, and on the right is zooming in on the lowest 2 kilometers. And this plot here, this example here was really impressive to me, mainly because, so you can see with the dashed line what the ensemble mean for the constraint looked like in both temperature and water vapor. And it doesn't look like it's deviating too much from the ensemble mean. But at the lowest levels, you can see that the ensemble mean was too warm and didn't represent this weird temperature inversion and feature in the lowest 500 meters. But when we add that ensemble mean with the AERI forecast, with the AERI data, we're able to capture that weird temperature feature from 0 to 500 meters quite well. Now, the sharpness of the inversion isn't as great as it is with the Radiosonde, but that's still a very impressive retrieval for capturing a very interesting feature like this. And then we're able to get that retrieval to look decent all the way up to the top of the troposphere because we're having that ensemble constraint things where we don't really have information from the observations. Looking at water vapor, it's even more impressive because when you look at what the water vapor profiles look like from the AERI, they're quite biased too high at low levels and also too high in the mid levels. But just using the AERI and information from the ensemble, the AERI is able to add information that, yes, there should be a little bit more water vapor at low levels than what the profile is. Normally, the AERI is not going to be able to put in that much detail in the water vapor field, but because it doesn't need to really recreate the shape of the profile, just needs to be able to add and subtract in regions, it really ends up producing a good water vapor profile. And again, I want to point out that this is just using the AERI and then information from a model. That's just one instrument, but I haven't yet tested it when combining multiple instruments into this type of retrieval. And then I'm just going to go through the other radiosondes for this day, and you can see that the results are pretty much the same for the other cases where we have really good temperature retrievals and really good water vapor retrievals by just using that AERI and Ensemble constraint. This last profile, the water vapor, it maybe isn't as good as the previous two, but again, it's still better than what the AERI produced on its own. And it still gives more information at low levels on what the water vapor profile looks like than what the Ensemble produced on its own. So I'm really hopeful that this method of using an Ensemble constraint in these thermodynamic retrievals at these kind of profiling sites is going to be a really key feature of the data products that we want to develop in these networks. And so now we're going to look at the window E with the Ensemble constraint. And again, it works similar to the temperature retrievals, but in regions where we're most uncertain, the observations should help us the most. And regions where we aren't that certain in the observations, the Ensemble is going to help bring the retrieval closer to what it should be. And that you can see that's the case here, where the blue line is what was retrieved with no Ensemble constraint. The reason I'm not showing what's going on when I don't use Ensemble constraint above the height of the maximum data level is because the retrieval is just so bad that it's really not worth showing. But when we add in that Ensemble constraint and that the Ensemble can kind of guide what's going on in regions where we may have low information, you can see that the profiles match quite well with what the Radiosonde was observing. And then for the other cases, it's pretty much the same thing. There are times where the profile is really just what the model is showing, but that's not always a problem because it still is useful, at least I believe it's still useful, to be able to have a full connected profile from your observations to your mid-levels and even to the top of your atmosphere as a way to really see what is going on at a site. So yes, it might not be consistently observed from one specific instrument, and it may be combining the modeling and the observations, and you might be focusing more on one at one time and more on the other at the other time. But I don't see that as a potential issue because you're still going to want to know that information at some point. And most of the time, someone's going to just be looking at an analysis or a model anyway to figure out what was going on at those levels where the observations weren't able to capture. So this is, and then this last one, you can see how the Ensemble wasn't really doing the low levels very well, at least in the U component. But then the observations where we had lots of LiDAR obs, the tower obs, they were able to pull away from what the Ensemble mean did to what the sonde was showing. But then the Ensemble was able to help constrain at the mid levels where the wind profile was starting to have some difficulties and pull the data back towards what the profile was looking like there too. So again, I was very happy with how these Ensemble constraint profiles were turning out. They actually were much better than I even could have imagined them going up to. And then I wanted to show, revisit that window E full day profile, time height plot at this site where we were, and just show kind of what we're able to then capture and see when we have that Ensemble constraint there. And yeah, there is some choppiness in the retrieval, mainly because we're adding a different constraint in every hour. And maybe in the future, we look at better ways to merge these constraints, maybe kind of use a time lag ensemble so that the constraint isn't changing as much or as drastically with time. but you can see the improvement over that initial profile where we didn't have that model constraint. It just helps smooth out noise and also gives you information above where you have observations. Where I see this as very useful, that you can connect where you have the observations and what could be going on at upper levels at one point, which is a great thing for a potential end user to not have to go searching for, well, I know what my observations were saying going on with 2 kilometers, but is there anything I can get from what was going on at mid levels? So I see this as a potentially useful product in the future as well. And then the last thing from this I wanted to show is just that using just the AERI, the Ensemble constraint, and then the tower wind profiler and Doppler LiDAR observations with the Ensemble constraint, we can get pretty accurate SKUTs at a site without ever launching a radiosonde. And I'm only going to show 3 SKUTs because these are the ones that I ran the retrievals for. But ideally, you could run these retrievals every 5-10 minutes and get rapidly updating SKUTs for the whole day without ever launching a radiosonde. And you can see that the evolution of that boundary layer through that afternoon quite well, and the change in the winds with time. So I think this is a very exciting data product that could be used at these profiling sites. So now, in summary, next generation boundary layer observation networks are an important next step for boundary layer sensing. And these networks are going to require the development of quite a bit of integrated data products. And what I showed today is just a very small step in kind of what needs to be done in order to use these observation networks in the best way possible. But TropoE and WindowE could be 2 tools that can be used for high temporal resolution thermodynamic and kinematic profiling at the profiling nodes for these networks, since these algorithms can combine the information from the different observations so well. Our proof of concept testing also suggests that using an NWP ensemble constraint in both TropoE and WindowE can significantly improve the results of those retrievals. And this suggests that the networks would be really well complemented by a dedicated ensemble system. And that, again, that's a big thing that I think needs to be included in these boundary layer observation networks, is that we really need to start combining how can we integrate these models into what we're doing in these observation networks to create the best, give people the best information about the state of the atmosphere that we possibly can. So with that, I can start taking any questions. But before I do, I just wanted to show this plot of 10-second wind retrievals from the Doppler LiDAR at OU. It was sitting in the vehicle bay in a tornadic environment, and we figured why not try to spin the LiDAR as fast as possible and retrieve what the wind's doing. And so this wind retrieval is actually done with WindowE, and the reason it was done with WindowE is because it does so well at help smoothing out the noise from the rapid wind retrievals rather than just calculating the individual profiles from a direct VAD analysis. I thought the plot looked cool, and the wind color, the color bar, is really satisfying to my eye. So I thought it was a good question slide plot. So with that, I can take any questions.
I have to remember. Great. Well, thank you, Josh, for an excellent talk, merging observations from a suite of sensors to capture a holistic view of the boundary layer profiles. And I should mention you are a trooper, and you get a gold star for giving a seminar when you are not feeling so well. So we do have time for questions and comments. May I remind the audience to please use the Slido interface below the presentation screen to ask your questions. And we have a question from a colleague, Tammy Weckworth, who works with the MPD, we all know. And she says, thanks, Josh, for a great talk. Will you please say more about potential causes for AERI MWR MPD temperature retrieval bias. I'm puzzled how it could be due to an AERI calibration issue, particularly because both the AERI MWR MPD water vapor and the AERI Ensemble constraint retrievals look so good.
Yeah, it's a puzzling thing when you think about it. I should also say it could also be due to an NWR calibration issue too, since the problem is also when you add in the microwave radiometer. But the reason I think it could possibly be a calibration issue, even though the AERI and Ensemble constraint retrievals look good, is because in the AERI and MWP, when the Micropulse Dial is added to the observation vector, most of the information content is going into just the water vapor field. There is a little bit of information that goes into the temperature profile, but what could be happening is that the AERI, if it's biased, it is so constrained in the water vapor, and it can't kind of balance out the fact that the water vapor profile that it's retrieving, because the MPD is there, doesn't match up with what the radiances it's observing. So the radiances from the profile, the forward operator radiances, look really different with the MPD than when the MPD isn't there. And because of that, it has to do something to adjust those radiances to what it thinks it should be, and that's to crank up the temperature at those heights. That's just my working theory about what could be going on. And the reason it doesn't show up as much in the AERI and Ensemble constraint is because when the Ensemble constraint's there, the information is spread equally between between water vapor and temperature. So now we have the temperature field is more constrained and the water vapor field is more constrained. So even though the AERI might be still biased, the Ensemble is providing such a strong constraint, especially since the Ensemble does not allow for much variability at those levels, because there just naturally isn't much variability in the Ensemble at those heights, because temperature isn't that variable at those. There's not much spread in the Ensemble. So the AERI really can't pull the temperature too warm at those heights because the Ensemble is preventing it from doing that. So that's my current working theory, is that it's really because dumping all the information in the water vapor is just making it really tough for the AERI to justify what's going on with the temperature when it has potentially biased radiances.
Thank you. Thank you, Tammy, for that question. We have a question from Craig Ferguson, who asks, have you or others identified candidate sites where Lotus facilities would add the most value? Perhaps the HER-RAP team has identified geographic regions with systematic poor model performance in pre-storm environments.
So I don't know if we've specifically discussed regions where we have poor model performance that it might work out, at least not, maybe a little bit at my time at EOL, but I do know that since working at CERO, these type of next generation boundary layer networks, or Lotus, have the potential to be extremely useful, or we believe it could be extremely useful in the Southeast United States in their severe storm environments. There's been a lot of Aussie work at NSSL and CERO into how would these observations improve the Warn-On forecast system. So I know that's one reason where we believe that having this type of network would really improve things. And beyond just for modeling capabilities, this type of network could be really good for nowcasting for forecast offices and things like that. So there's lots of potential uses for how these networks could be beneficial to both in the forecasting perspective.
Thank you for that question. We have a question from Terry Hoke, manager at ISF. who says, great presentation, Josh. What do you see as challenges in combining UAS in situ data and the value in UAS data in combination with all the other instrumentation?
Yeah, so when I think about UAS data, it is probably, depending on the type of UAS, one of the more difficult things of how do we put this in properly. When you think about fixed wing aircraft, it's just a little bit different in terms of combining that information into a single profile, because it's collecting more spatial information than you might than a vertical profile. Now, the UASs that are like copter sondes, those can very easily be combined in value with the observations that we have from the other instruments. But I do see kind of balancing that spatial and time information from fixed wing UAS as quite a difficult problem, just because you have to account for the UAS may be hundreds of meters away from the center point of your profiling node, and it's constantly changing position with time. And how do you balance that information into, say, a profile? And so maybe UAS, fixed wing UAS, are not something that's going to be the most valuable for profiling, but maybe fixed wing UAS will be very useful for giving us information on turbulence around the profiling sites or things like that.
Thank you for that question, Terry. And we have a question from Steve Ongley. And he asks, good to see you again, Josh. Sorry you're not feeling better. I'm trying to imagine how the wind and TQ retrievals could work together. Perhaps try to tie everything together, calculating Richardson numbers. Have you given this any thought?
So it's interesting you mentioned combining wind and temperature retrievals. And I can't really take credit for this. This is actually, but I'm going to mention it in a meeting that I had with Dave Turner, is that it should be theoretically possible to actually combine wind and temperature retrievals together to help constrain both of them. You can kind of think of it as the idea is that if you're in like a post-frontal flow, you should know that your temperature profile at low levels should be cooler when you have northerly winds over southerly winds and things like that. So there is a possibility to really make the wind and temperature retrievals work together. I haven't thought about, I mean, those wind and temperature profiles in terms of just calculating things, you could definitely calculate Richardson numbers from those wind and temperature profiles that I showed on the at the end on those QTs. You can really start to calculate a lot of those kind of. So the nice thing, and the reason I like to show the full profile with the ensemble constraint, is because it really gives you the opportunity to do things like calculate Richardson numbers, or beyond just kind of boundary observations. Now that you have that full profile, it gives you the opportunity to calculate things like maybe storm relative helicity or CAPE or SYN, or all sorts of different full kind of integrated quantities associated with those profiles. So it really is possible to do more where we're working with the wind and temperature fields and doing it together, but I haven't got there yet.
Work in progress. Thank you, Steve. It was good to see you attending the seminar. Okay. We have a question from Junghyun K, and he asks, it was a really great talk. I have two questions. One, when combining different profiles, how did you calculate the error covariance of each observation? And two, in the lower atmosphere, especially near the surface, the ensemble spread tends to be very small. Did your ensemble maintain a large spread?
Yeah, so for calculating the error covariance of each observation, the first thing is that each observation, the covariances between them, we're assuming are zero. So there's no off diagonal elements for the error covariances of the observations, which is an assumption, but that's currently just what we're working with. It makes the retrieval math a lot easier. And it's hard to figure out what actually should be those covariances. It's a difficult problem. And for my ensemble spread, near the surface, the spread, and because of the way that we use stochastic physics, the spread wasn't huge. My ensemble did not have a large spread at all. In fact, it was definitely, I would say, under-dispersive. It probably did not accurately capture the proper spread that it should be. But that's also why I was very happy with how things turned out, is because even I was worried that the spread was going to be so small that the AERI wasn't going to be able to do anything to the profile. But even in a case where there wasn't the largest amount of spread, it still was able to pull the ensemble forecast from what it was saying to what the observations were showing. So no, my ensemble did not have huge spread, but it's something that would have to be worked on when kind of creating an ensemble system for these types of observation networks.
Great. Thank you, Jung-Kyung. With no further questions, we are past the seminar hour. If you are interested in Dr. Josh Gebauer's presentation and have further questions or want to collaborate, please reach out to him via his email, which should be provided on the seminar flyer. On behalf of EOL, I would like to thank Dr. Gebauer for his talk in improving boundary layer observations or profiling by leveraging our current suite of profiling instruments. Thank you, everyone, and have a good day.